The Center for Energy Nanoscience is an energy frontier research center located at the University of Southern California and was formed out of a mutual interest among the faculty at various universities to try to develop a better understanding of the phenomena that control the efficiency and ultimately the cost of solar cells and light-emitting diodes. The center is emphasizing solar energy because, after all, the sun is an inexhaustible supply of energy. But unfortunately, the cost of the technology right now inhibits its use. The center was organized around the idea that we would develop the fundamental understanding necessary to have breakthroughs in the efficiency and cost of these devices. The center also has a strong effort in the development of efficient light-emitting diodes for general-purpose lighting. The technologies for light-emitting diodes that we're developing have the prospect of improving the efficiency of light sources by a factor of 10. If we can achieve that, we'll reduce the amount of fossil fuels that we need to consume in the world to generate light.
In our center, we're working on a number of things that will significantly impact the efficiencies of solar cells and organic LEDs. Organic photovoltaics are a very important area to work in. Organic devices have a number of benefits that traditional inorganic cells don't have. We can prepare organic cells on virtually any substrate: glass, plastic, metal foils, even paper, which gives a lot of new areas you could think about deploying solar cells that you couldn't with a traditional cell. An interesting component of organics is that you can think of them really as modular components, that we can swap out one organic material for another and look at the devices as a function of this material substitution. We spend a lot of our time trying to understand how an LED or a solar cell actually works, thinking of it on the more sort of microscopic scale. What are the individual steps that are involved in each of these processes? And once we understand those, we can start designing materials that optimize each of the individual steps. And so we spend most of our time trying to really understand the detailed mechanism. And the more detailed the mechanism we can draw, the better the model is we have for this device, the better we can get the device to perform.
At the Center of Energy Nanoscience, we have some very detailed characterization techniques. Nonlinear spectroscopy to actually characterize buried surfaces, femtosecond time resolve techniques to actually uncover each of the steps of the cascade of electronic processes, and detailed theoretical simulation. In the center, we use molecular design to essentially manipulate each of the fundamental processes that are going on inside a material. With this type of characterization, we can pick apart each of the fundamental steps. To give you some examples, we want to actually be able to look at charge carrier generation and make sure that that's highly efficient. And also, if we are able to achieve exciton multiplication, we need to be able to actually see what material design characteristics lead to higher numbers of excitation splitting in organic, photovoltaics, and LEDs. We can extend the range of light that's being harvested into the near-infrared by changing polymer design to include extra donor acceptor groups. We can engineer the morphology of molecular materials to enable processes like singlet fission or triplet annihilation, respectively, in photovoltaics. These are all new elements that can be brought to bear to increase the efficiency of a given material in its device.
An important component of our research is designing optimal solar cell structures and predicting what efficiencies they will have. We use the computing capabilities here at USC to do both these things. We can tell experimentalists what we think the best structures might be to achieve high efficiencies. And then we can also help interpret experimental results or experimental measurements by relating those measurements to the fundamental material properties. The high-performance supercomputing facility that we have at USC is very important to the efforts of our center. The facility itself has more than 1 million cores available for processing. And that means that we can take large simulations and split them up to run on multiple processors at the same time. This is important both for modeling at the atomistic level as well as the level of light interaction with nanostructures. We are currently performing experiments to show that nanowire structures are more absorptive than solid films. On the atomistic level, researchers are using simulations to understand how nanostructures form atom by atom, and help understand the conditions under which we can grow defect-free structures. On the larger scale, simulations have been used to design the structures that absorb the most light and provide the highest solar efficiency.
The avenues that we're pursuing within the Center for Energy Nanoscience are in some sense unique. They involve unique structures and unique platforms for both solar cells and for LEDs. In addition to that, we have some of the world experts in both of those areas within the center. I think we have the prospect of making great breakthroughs in these areas that will advance the technology of both solar energy and solid-state lighting.